You can see my cursor as well, right?
Yes, I can see very well.
Okay. And is the slide moving?
Yes, slides are moving perfect. Everything looks okay.
Okay.
Thanks. That's good.
Yeah, good.
So yeah,
Yeah,
so
so you're
actually
saying...
we may wait like. No, I was telling that maybe we can wait a couple of minutes. Maybe we can wait a couple of minutes because some people join slowly.
Yeah,
okay.
Sure. How's the situation there? Is everything functioning well, the office? Or you're working from home?
Yeah. So more or less like we are like still in the hybrid mode, working from home as well as like we come to office also.
Okay.
So but things have returning to the normalcy.
Oh, okay. So
cases
are minimal.
Sorry?
Number of cases are quite minimal.
No, now it's almost zero. Not many. We have even less than 10 live every day, I guess.
Oh, okay. That's very
good.
It's
yes.
Yeah, happy to hear that. When did you join there?
I joined in this last year, December.
Okay.
Yeah. Okay, so if everyone can hear me, let us wait a couple of minutes before other people are joining. We'll start maybe around 3:32 or 3:33.
Hello, Jessy.
Hi, Saurav. How are you?
Yeah, fine.
Okay. Yeah, happy to see you. How is the weather there? Is the DOT running every day basis?
Yes, this year lot of rain. So, but in October we'll see.
Yeah.
Still raining. Today is 14th. So
yeah.
Usually in September first week, this monsoon goes away. But this year, 10 days more. So,
Right. So observatories are kind of shut down, all the telescopes.
Yeah, closed.
Okay.
So from June to September 30th is closed.
Yeah.
Okay, so hello everyone. I think we can start now. Welcome to the weekly seminar series at IISER. We are happy to have Dr. Jessy Jose today. Very briefly giving you introducing the speaker. Dr. Jessy Jose is not a new person at IISER. She has done PhD from here with the late Professor A.K. Pandey. In 2012. After doing her PhD, she did a 2-year postdoc at Indian Institute of Astrophysics in Bangalore. And then later she went to Beijing at Cowley Institute of Astronomy and Astrophysics, where she did her second postdoc. And since 2017, she is an assistant professor at Indian Institute of Science Education and Research, Tirupati. She is also a member of Astronomical Society of India, American Astronomical Society, and the International Astronomical Union. And she is also an IUCA Associate since 2018. She is the recipient of the Outstanding Postdoctoral Fellow Award at Peking University in Beijing. And her research interest includes multi-wavelength observational studies of star-forming regions, brown dwarfs, and free-floating planetary-mass objects, protoplanetary disk properties of young stellar objects, star formation under low metallicity environment. So welcome, Jessy. We are happy to have you here. Seminar will be around 45-minute duration, and so you can start now, and I will give you a reminder 40 minutes from now. Please, go ahead.
Thanks a lot, Vaidehi. Thanks a lot for having me here and giving me an opportunity to present my work. It's always I'm happy to be known as part of Aries group. I have always sweet memories of Aries, like a lot of friends, a lot of seniors. So I wish I could come there personally and give this talk. So, all right. So today I'll be talking about brown dwarfs and free-floating planetary mass objects, some of our recent analysis on this topic. So I like to call these candidates as our coolest and youngest neighbors. Coolest because they are very quite low temperature of the order of thousands of Kelvin or lower than that. And there I'll be talking about the youngest such objects, so of the order of few million years age. And neighbors because these are we have studied some of the nearby star forming regions which are essentially close to solar neighborhood and within 500 to 500 parsec to 1 kiloparsec. So they are the closest and youngest and coolest neighbors of us. So this is a collaborative attempt with this international team as well as postdoc and few students at the IISER Tirupati. Yeah, here is a brief outline of my talk. I'll be talking about the brown dwarfs, its a basic definition, and free-floating planetary mass objects and their characteristics, and the need of understanding them. Why do we need to study them? How to the main technique? What are the different techniques to detect and identify and classify them? And then I'll be talking about survey of nearby star forming regions and preliminary results. Couple of papers are already published on the survey. I'll be talking about them, and the survey is ongoing. So I have basically the preliminary results to present here. Before moving on, let me introduce the various stages of star formation. I'm sure you would have seen this slide 1,000 times at Aries. Just to revise the number of stages or various stages of star formation, we all know that star formation happens in the dense molecular cloud. And when it undergoes gravitational fragmentation, it go through like one of the components, if you consider this go through the gravitational collapse. And then most of its mass settle down into the protostar form. And then matter will be there will be matter around the protostar in the form of protoplanetary disk and huge envelope. Later on, most of its mass in the envelope gets settled down into the center protostar or in the form of protoplanetary disk. Eventually, along this protoplanetary disk, the planets are formed, planets of various sizes and properties, they form along the protoplanetary disk. And finally, the disk almost dissipates, and then a solar system kind of planetary system evolves out of this. So when the central massive central star starts burning hydrogen, then we call it as a star, and the planets revolve around the central star. Because this is a typical scenario of low mass star formation. Low mass, when I like to highlight, is like of the order of a few times solar mass, like 2 to 3 times of solar mass, and much lower than that. So these low mass objects mainly follow this scenario. Now let's see the basic definition of low mass objects. I will be addressing, as I mentioned, I'll be addressing about the very low mass end. So what is the end of that star formation or limit of the star formation? So let me revise the basic definition of star and brown dwarf and planets once again. So any object, we all are familiar with this basic definition. Any object which can burn hydrogen in their core, they are called star, any celestial objects. But those objects which cannot burn hydrogen and mass less than 72 Jupiter mass, and which can burn deuterium instead of hydrogen, deuterium in their core, they can be called as brown dwarfs. And those objects which are less than 13 Jupiter mass, and which if they do not burn deuterium in their core, instead they orbit, if they're orbiting around a central star, around the central star, mass less than 13 Jupiter mass, then we call it as a planet. But those objects which are again less than 13 Jupiter mass, but do not have a central host star to revolve around, and instead they are like free to move around, there is no host star, then we call them as isolated planetary mass object. So these are like a free floating. We can call it as free floating because they do not have a central host star. They are just like a planetary mass object. Their mass is less than 13 Jupiter mass. They are just like planets, very low massive, very low temperature, and they do not have a central host star. So in this talk, I'll be mainly addressing these two type of objects, brown dwarfs and free floating planetary mass objects. These are the low mass end of star forming event, the extreme low mass end of star forming event. Okay, so coming to some of the characteristics of these low mass objects. They are self-gravitating object and self-luminous. So their core temperature is not sufficient to burn hydrogen. The temperature is always, since it is not sufficient, the temperature is not enough to burn the hydrogen. The temperature is always less than 3 into 10 to the power 6 Kelvin. And their mass ranges, as I mentioned, it's between 0.01 to 0.72. So here on the left side, I have shown the temperature versus time scale of these different types of objects. So these dashed lines are the temperature limit for the deuterium burning, lithium burning, and hydrogen burning. So as I mentioned, those objects above 0.072 solar mass can eventually burn hydrogen in their core, and then they are like a stable main sequence star. But those objects which are within 0.07 to 0.012, they essentially burn deuterium. And the heavier mass of them, so the upper end of these range is called the brown dwarf limit. And among brown dwarfs, the heavier ones, like of the order of between 0.06 to 0.7 solar mass, they can burn lithium in the initial stage of their lifetime in their core. And their spectral features, which I'll come later in detail, they're mainly their atmosphere is filled with the molecular bands in their stellar atmosphere. Or if you look at the spectral features, they are mainly molecular bands. And their first prediction of this kind of objects was by Shiv S. Kumar in 1963. This was a theoretical prediction. And it took another nearly 3 decades time scale to observationally confirm the presence of brown dwarfs and such free-floating planetary mass objects. That was in the very first discovery was by Robolo et al. In 1995. And as I mentioned, these are like a constantly cooling objects. So on the right side, this plot is nothing but again the evolutionary tracks of various types of objects. So the red curves are the stars, which will stabilize its luminosity because they can burn hydrogen in their core. And then these brown curves are the curves for the brown dwarfs, evolutionary tracks essentially. So age versus effective temperature. So as a function of age, how this brown dwarfs can evolve. And these are the planets. These are the curves for the planets. So you can see on the rightmost axis, I have given the various spectral class of them. So the brown dwarfs can be it starts the spectral class. The earliest one is late M type stars. So starting from M6, M7, M8, M9, and so on. And then the other spectral classes are L, T, and Y dwarfs. But these are like the evolutionary track. So if you follow one of these tracks, this brown dwarf starts in the very early stage as a late M-type star, but eventually it ends up as T dwarfs or Y dwarfs. So this with the evolution, they change their spectral class. This is a very unique feature of these low mass objects. Okay, and another important feature from this diagram is they are there at a very high temperature when in the very initial phase, because it's just would have formed out of the molecular cloud. So it's a gravitationally still contracting object. So in the initial phase, they'll be bright and high temperature when compared to very old stage. So it's about age. If you consider a 10 giga-year brown dwarf, they are much low luminous and low temperature when compared to in the initial time period. So it's easy or relatively since these objects are relatively brighter at the younger age, it's important to catch them when they are young because they are bright. Otherwise, they go very deep, and it's really difficult to catch them when they are really old. So star forming region, in that context, star forming regions are the ideal size to understand these properties of these objects. Okay, so coming back to the classification again, brown dwarfs essentially bridge the gap between stars and planets. This is the temperature scale. and they essentially share similar properties, like they share the properties of stars and planets. So for example, stars are self-luminous. These brown dwarfs are also self-luminous objects. And they also, some of them have shown evidences of disk and outflows. These are the characteristics of stars itself, young stellar objects, young stars. But some of the brown dwarfs, young brown dwarfs, also show similar characteristics. And stars can be multiple in binary system or tertiary system, and there are evidences of brown dwarfs with the companions in binary system. So they form, they share some of the properties of stars, and at the same time they share the properties of giant planets, also exoplanets. Especially they have very cool atmosphere, they have strong molecular bands in their atmosphere. So all these are the essential characteristics of giant planets. So and also what are one of the most important aspect of studying this extreme low mass objects or brown dwarfs are they are similar to, they are ideal laboratories for exoplanet studies. Nowadays exoplanet studies are so hot, but the main challenge in exoplanet study is direct imaging studies is very challenging, because you have a very bright host star, so you have to mask it and then you have to monitor the surrounding revolving planets. So that's a direct imaging technique. But these objects are very similar to exoplanet or giant exoplanets, but they don't have a host star to block them or to block their visibility. So these are like ideal targets. If someone wants to study the exoplanets, they share the similar properties. Now coming to the spectral features, as I mentioned, they are essentially into four. We can classify them into four spectral class. Late M types. So late, I want to say that it starts from M6 and later. So M6, M7, M8, and so on. And L type brown dwarfs, T types, and Y dwarfs. So as age goes, they evolve from one spectral type to other one. On the left side, I have shown some sample spectra of these brown dwarfs taken from Allers and Liu 2013. So you can see how the spectral features varies as a function of spectral class. So this one is for M5, M6, and M9, then L0 up to L6 I have shown. So you can see the black body, how it varies as a function of temperature or spectral class. So initially the black body peaks at about a J band or 1 micron, and then in the later class it peaks towards the longer wavelength. And also the spectral features, if you see, there is a strong absorption band H2O and FEH features. These are the important features of this kind of objects. But as you go to the late classes, this strong absorption, water absorption feature, it keeps on coming down, or it is like a more strong towards the later type. Here also it's more strong. So towards the later type of late L type, the water absorption strength increases. So some of the features I have shown here, late M type stars show the features like a TIO, VO, molecular bands, and some of the alkaline lines as well. L type have like a strong H2 absorption bands as well as VO bands in their models in their atmospheric spectra. T type have methane absorption feature. This is also a strong feature in the near infrared regime, and then also it has H2O features, H2O strong absorption band in their spectra. Y type has essentially NH3 absorption feature. So these are the basic spectral characteristics of these objects. And where are they located in the HR diagram? So if you keep them on the HR diagram, this is the extreme, this extreme end of, or extreme right and bottom end of HR diagram is the location of brown dwarfs. They are very cool, they're very red, and they are very low luminous object. On the right side, you can see this is an empirical diagram, empirical sequence of all the low mass objects compiled by Bailey in 2014. So on the x-axis, it's a spectral type versus temperature. So you can see there is a discrepancy where you have instead of a direct sequence, there is a kink or some discrepancy in the LT transition range, which is one of the unknown problem or unsolved problems in astrophysics or in this area. Nobody knows why there is a transition and where there is a discrepancy in this particular curve. Otherwise, it's the temperature wise, it's they're all like less than 3000 Kelvin, and they belong to this class, spectral class. So now coming to their various formation scenario. So I just explained that the stars are forming out of the gravitational contraction of the molecular cores, just direct collapse. Then that will lead to stars. Whereas planets are essentially formed at the protoplanetary disk or surrounding disk, circumstellar disk of young stars. That's a formation scenario. But how about the brown dwarfs? The brown dwarfs have like people have been proposing several scenarios for the formation of brown dwarfs. The major 4 ones I've addressed here. There are many scenarios suggested in the literature. I've addressed only the main, the 4 scenarios which are like well acknowledged in literature. So they are turbulent fragmentation, dynamical ejection, disk fragmentation, and external photo erosion. Coming to individual formation scenario, the first, one of the scenarios proposed for the low-mass stars and brown dwarf formation theory by Padovan and Norland in 2002 and 2004, they're nothing but it's just a scaled down version of low-mass stars. So we just see how the low-mass stars take place, right? The same way this brown dwarfs or this free-floating planetary mass objects, they form out of the fragmentation of the hierarchical fragmentation of the molecular cloud, and the smallest cloud, the smallest core end up as brown dwarfs because they are very small. They fragmented as small, and then they have very less mass to accrete finally to accrete to the center of proto system or proto brown dwarf, and finally they end up having very low mass. They evolve as a very low mass object. So that is just like a scaled down version of the low mass star. And the another scenario proposed is the dynamical ejection scenario, which is proposed by Raypooth and Clark in 2001, later confirmed theoretically by Bate et al. In 2003 and 2009. So they say that it's out of this is purely because of the dynamical interaction. So where you have a massive star forming region, lot of massive fragments or cores are there, they go through dynamical interaction, in-body interaction, and then as a result, because of the interaction between different cores and all, these small tiny guys, they get ejected out of the system. Once they're out of the natal molecular cloud, they have very less amount of matter around them, and then they end up as a very low massive brown dwarf. So this is one of the like well accepted scenario for brown dwarf formation. And the third scenario is about the disk fragmentation. So just now we saw that there are protoplanetary disk around the central protostar. So this the brown dwarf starts their life just like a planet around in the protoplanetary disk of this host star or central protostar. And then they eventually, because of the disk asymmetry, they eventually accumulate more massive. Once they are relatively massive when compared to our own planets in the solar system, when they are relatively massive, there is no more stability in their disk, and then they will be ejected out of the system. So it's just a disk fragmentation. They're formed in the disk, and then they eventually get ejected out of the disk due to instability. And this has been proposed by Bate et al. In 2002. The last scenario, well accepted scenario, is the photo erosion method, where you have OB stars, massive star forming regions, and when there is a massive star, we all know that it gives out UV radiation, strong stellar winds, etc. So this tiny fragment, tiny core in the star forming region, they will be photo eroded because of the presence of strong stellar winds and UV radiation from massive stars. As a result, there are like a lot of material around this object can be removed, and then they finally end up as a low mass, extreme low mass object. So this is the fourth scenario, which is well acknowledged in the literature. So now, why do we care about such objects? Like they are, first of all, they're very low massive, low luminous. Why do we need to care? So these are the unsolved issues, or which I like to address. I'm not claiming that I'll be getting an answer for all these problems, but I just want to mention that these are the main scientific goals of this particular survey program. So this is to explore the low mass end of initial mass function, their dominant formation mechanism. Is there any preferred formation mechanism for this kind of objects? Do they also have disk around these low mass objects? Do they possess disk around them just like stars? And do they have, what fraction of them have companions with them? And finally, do they form differently in different environmental conditions? So these are the main scientific goals of this survey program. So let's see. So we all know that in a star forming event, there are like thousands and hundreds and thousands of stars are formed out of a molecular cloud. And some they all have wide variety of properties in terms of their mass, in terms of temperature, luminosity. Some of them are very bright objects, some of them are very low luminous, like brown dwarfs, which we already saw. So this is a typical example of a star forming region. It's a near infrared image of M17, which is one of the very dense, rich cluster in our galaxy. So I want to show you that this kind of star forming regions have objects which have wide range of properties, physical properties. Not only the member stars of this region, they have foreground contaminants as well as the background contaminants. So in such kind of regions, it's very challenging to identify this low mass objects or extreme fainter end of the low mass object. So if you consider the initial mass function or the stellar mass spectrum of the nearby region, so this is on the left side, it's for the nearby star forming regions initial mass function, and on the right side is the initial mass function of the relatively old cluster and of globular cluster. So they essentially follow the salpeter IMF in the higher mass end, and there is a break somewhere around 0.7 to 0.5 solar mass, and then there is a turnover towards the lower mass end. So on the y-axis is the number of objects versus the logarithmic mass of the objects. So why I want to highlight this, towards the fainter end or towards the extreme low mass end, we have very less number of statistics, or the IMF is very poorly constrained towards the low mass end. So because of the limitations in identifying them or detecting them, we don't even know what is the limiting mass which can be formed out of a molecular cloud. So there are a lot of uncertainty towards the fainter end. So this is I would like to highlight one of our recent study by Belintama in my group. So we have covered several star forming regions in the Milky Way, and we obtained a representative IMF for all of them. But I want to, and on the right side, it's the IMF variation as a function of UV radiation and stellar density of the underlying cluster and the galactocentric distance. So this is the critical mass. This highlighted portion is the critical, or the critical mass of the IMF, you can say, or peak mass of the IMF. So we didn't find any variation of IMF as a function of these physical parameters of the underlying background. But what I want to see, we still do not have this kind of regions. We do not have, or we are unable to cover the extreme low mass end of the IMF. So that is purely the current limitations of our survey, and we need to explore what is the form of IMF at a different environmental conditions. So now the big question, how to detect, identify these kind of brown dwarfs or low mass objects. Again, the biggest challenge in such star forming regions are their high reddening. The reddening can be like of the order of few magnitudes in visual band to few tens of magnitudes. So in such a highly reddened medium, it's always challenging to separate out or to detect or identify. And you have a large pool of stars, thousands of stars in a given star forming region. So it's really difficult to identify them in such an environment. So here I would like to highlight some of the methods. What are the various methods which can be used to characterize or to identify the brown dwarfs? So first method is obviously the spectroscopy. So if you have a dedicated telescope and a very high sensitive telescope, we can, spectroscopy is the direct method to characterize them. So we have the spectral feature. Once you have the spectra, you essentially match the spectra with the model, either with the model atmosphere spectra or with the standard spectra of non-spectral class, and then by varying distance or extinction and other parameters, free parameters, and then the best chi-square match you will get as the spectral type. So that is the direct method. But in a star forming regions where you have thousands of stars, so it's practically not very easy to get the spectra. It's very time expensive for bigger class telescope. We need bigger class because they are very faint objects. Also, extinction is very high in this kind of regions. The next method is by multi-band SCD analysis. So if you have broadband photometry for say at least 5 to 7 bands, then you can fit the SCD by using again stellar models, and that best fit model will give you the stellar parameters like mass, age, temperature, luminosity, etc. So at least you need to cover this peak. This is a typical SCD of a brown dwarf, which peaks at about JH bands, and but you need the observation in at least 5-6 bands, so including the optical bands. So again, since these are faint objects, getting this longer wavelength observations for all the objects, it's quite challenging. So in order to perform a statistically meaningful analysis in star forming regions, there's both spectroscopy and multiband SCD, though they are the ideal methods, it's quite challenging for this kind of regions. So what is the like a possible solution for this? So here I would like to introduce a novel technique called W-band imaging, where you can separate out the brown dwarfs from the rest of the contaminants in a given star forming region. So what is W-band? W stands for water. So as I mentioned, these are very cooler objects and they have a lot of water content or molecular bands in their atmosphere. So they will be, since they have like a, you can consider they're like a clouds in their atmosphere, and then when they go through the radiation from this brown dwarfs, when they have to pass through their atmosphere, so that has been self-absorbed by the presence of water in their atmosphere and then reach to us. And in our atmosphere also we have our own issues, like our atmosphere also have water in the atmosphere, but yeah, so that I'm coming to that issue. But here what I want to say, these objects have a lot of water content in their atmosphere. So how do they look in their spectra? So this blue one, blue spectra is the typical brown dwarf spectra, and G2, the red spectra, is for a mean sequence counterpart G2 spectral class sun type star. So you can see this strong absorption band somewhere here at 1.4 micron, and somewhere here. These are the strong water band absorption because of the water content in their atmosphere. So if you essentially keep a filter, a narrow band filter called W band or water band filter at 1.4 micron, and if you monitor this object in J, W, and H, where J and H are the broad bands. So you can see here comes the J band and H band comes here, and water band. So if you monitor both the objects, this object will be hugely absorbed, self-absorbed in the water band, whereas it will be like equally bright in both the J and H bands. If this is of course a normalized spectra on the y-axis, it's normalized to the same signal, but this object will be, when compared to this G2 spectral type, this will be hugely absorbed in the W band. So that is a very easy technique to separate out the possible brown dwarf when compared to the background objects or the contaminants. For us, everything else other than brown dwarfs are contaminants in the field, so we want to separate them out. So this is an image which shows on the left side is a image of a brown dwarf in J band, and in the right side it's a image of the same brown dwarf in W band. So you can see, so it was quite bright in J band, but it's a self-absorbed. It's almost a negligible emission from the object in W band. But other stars, see, these field stars are similarly bright. So this is one like a very efficient method to screen these brown dwarfs in the star forming region. So what are the various telescopes or instruments which have W band capability or this narrow band filter? So far it's only with the 3 telescopes: UH 2.2 meter telescope in Hawaii, then HST a space telescope, and WireCam with the 3.6 meter Hawaii. So before, I think this capability or W-band technique or filter needs very dry conditions, because if you go to a moistured environment, then around sky will have a lot of water, and that will be like creating problems in the observations, or it will be the object will appear fainter, even more fainter, because of our own atmosphere. So we need relatively like a dry site like a Hawaii or Chile kind of thing in order to observe this object. This use this or in it's efficient in this kind of sites. We are dealing with a W-band water band imaging survey of nearby star forming regions with a broad game of goal to identify all the brown dwarfs and characterize them. Now, once you have the broadband photometry, so we need we need observations in this narrow band W band as well as broadband photometry in J and H bands. And we define as rendering insensitive index called Q, where this is J minus W plus E into H minus W, where E is a constant. And for those objects which are brown dwarfs or with a lot of water in their atmosphere, they have Q value less than minus 0.6. So all the objects, this is already like a proven, or it's a technique proven by all these previous studies by Allers and Liu in 2020 and 2030. Okay, so the background objects will have Q value greater than minus 0.6, and all these low mass objects, here again the caveat is both the candidate members and the background or field low mass objects also will have minus 0.6. Not only young brown dwarfs, everything in the line of sight will have Q minus 0.6, but they will essentially will be separated, or we can, by defining this Q index as minus 0.6, we can separate them out. They have a huge high value of high negative index, these low mass objects and brown dwarfs. We have tested this in the nearby star forming region IC 348, where the members are well known, and we have 90% confirmation in the IC 139 IC 348 star forming region. So these are the various star forming regions which we are surveying using this W band. And this is especially to the Taurus. Taurus, we all know it's a nearby nearby star forming region. It's about 140 parsec distant, but it's a large area coverage in the sky. So we are covering up to like a 27 square degree. This blue tiles are the area which we already covered, and the yellow tiles are the proposed regions for the CFST observations. And our survey is sensitive to like a 2 to 3 Jupiter mass. This is one of the deepest and widest search for the brown dwarfs in nearby star forming regions. So once you have the J and JH and W band photometry, so if you put them in the Kalamantu diagram, J versus J minus H, this is essentially the brown dwarfs. We cannot really distinguish. This curve is the isochrone of 3 million year for one of these star forming regions, and we cannot really distinguish the brown dwarfs from this pool of objects. But if you plot Q versus J, you can see that those sources, they are minus 0.6. They lie. There are objects with a less than minus 0.6 value, and then these are the possible candidates for candidate brown dwarfs for follow-up study. So once we have the photometry, we essentially need to have a follow-up observations. So we used all kind of spectroscopic capabilities, including 3-meter IRTF and our own 3.6. There was the optical telescope and Palomar and Subaru and all the bigger class telescope. And we also followed up using the Keck AO facility for the high resolution imaging. Similarly, HST WFC3 imaging for follow-up observations, like for high resolution observation. So these are the example, typical example of a brown dwarf, how it should be thing. Here I want to make an advertisement about the 3.3-meter IRTF, it's infrared telescope facility in NASA, owned by NASA in Hawaii. So this is an open telescope. Some of you might be already knowing. So I suggest the students, if you are looking for telescope time, this is one of the excellent facility, and it's open time. Anyone is allowed to submit their proposal, and which can be done remotely from anywhere. And they give freely account. They give training also for the observations before your run, and it's like a relatively easy observations. And we can very easily go up to J band 17 magnitude roughly for 1 hour observation. So it's one of the good facilities, I feel. And of course, it's a Hawaiian facility, so the night is clear there or with the less sea. So once you have the spectra, then you have to, as I mentioned, you have to match with the models or non-spectroscopy standard in order to characterize them. So this is one sample spectra. The black points are our own observation, and these are the model spectra, which we try to have a best fit. But remember, the extinction is so huge. This is one object in the Serpent South star-forming region. The extinction is so high; it's of the order of 15 and 12, it's of that range. So highly extincted low mass objects, but it's one of the youngest object. These are some sample spectra taken from Gemini and Palomar spectrograph. So on the left side, these are all young field dwarfs, young brown dwarfs, and these are relatively old brown dwarfs. So these are just a sample spectra which I wanted to show you. We also cross-checked with the Gaia information, where where are about their the promotion and other details. So most of the targets are, we do not have counterpart in Gaia for most of the objects, but whatever we have, they are agreeing with the general promotion of the brown the torus. So here is on the right side, it's a spatial distribution of brown dwarfs identified in torus. So here is another region, Sigma Ori, where I just want to show you a color magnitude diagram with a very well-defined pre-main sequence. So all these are the pre-main sequence objects, and these objects which are towards the this is Gaia color magnitude diagram. Gaia on the B band on the y-axis and B minus CFSTJ band on the x-axis. So you can see a well-defined pre-main sequence. And these low mass objects, we do not have Gaia counterpart for most of our new discoveries, but these are the spectroscopically confirmed low mass candidates, extreme low mass candidates in the Sigma Ori star forming region. We also checked, once you have the spectroscopic confirmation or membership, then we look for their further properties in longer wavelength. So on the bottom, this is HR diagram of samples selected in Serpent South star forming region. So you can see these are the new detections. Once you have this detection, we look for their longer wavelength properties. So this is one of the diagram which shows spectral type versus K minus W3 and K minus 8. These are the near mid-infrared bands. So those objects with a disk around them, they give infrared excess in the longer wavelength. And these 4 objects in the Serpent South, we have identified 6 of them. 4 out of 6 of them are showing near infrared excess property. So that is one of the scenario which we propose. They might be forming just like a scaled down version of low mass objects. That's why they have disk around them. So we are not finalizing on that statement, but this could be one of the scenario which we can confirm on Serpent's South star forming region. And we also look for the spectroscopy features. So one of the object we identified in Serpent's as with the Paschen beta and bracket gamma in emission, and we could obtain the accretion properties and accretion luminosity for this based on this emission line strength. So these are like one of the youngest and low mass object with accretion feature in our in the nearby world or nearby near to sun. So we had, as I mentioned, we had some HST follow-up observation, high resolution observation. So this is one such example. On top, this is on the left side top is a WFC3 UV's observation. The filter is F850LP low pass filter, and here it's the infrared filter F127, and you can see the size scale 0.2 versus 0.65. And this is for another object, a different object, its ID is given here. So on the left side, this is a high resolution image, and this is a lower resolution image. Both are with HST, so you can see an elongated feature. So we fit separately. This can be because of the possible companion of the brown dwarf. So we model this spectra, this image with the with the PSF fitting PSF on both the centers, and then we resolve them into a binary system. With the primary mass is about 0.08. solar mass and the secondary component between these two masses. But in the other filter, the near infrared filter, the resolution is poor, so we are unable to resolve them. So this is one of the separation between these companions are just 45 AU. So this is one of the closest companion and the low mass and youngest companion system or binary system in our in the nearby star forming region. So beyond solar neighborhood, so W band was using mainly for like a nearby star forming region. That's a limit, because we have to rely on the CFST capability. That's a 3.6 meter. So if you go beyond solar neighborhood, but we can't rely on the W band technique because of the sensitivity issue. So here it's a star forming region IC 1396. It's a R versus R minus Y color Mantoux diagram for this particular region. This photometry is taken from Subaru Hyper Supreme Cam. It's a one of the wide field. It's a 1.5 degree field of view detector optical imager. So it's a 8-meter class telescope. So it's a sensitivity is very enormous. So you can see your R band sensitivity is up to 26 magnitude. So we had the deep UKITS JHK photometry and optical photometry 4-band optical 4 bands plus UKITS 3 bands. So we fit the SCD analysis. Remember I told you that one of the methods to classify them using SCD model. So we had the deeper optical observation and then JHK. So we could get the SCD based membership analysis for these regions, where these yellow sources are the Gaia identified members, and this low mass objects, this fainter and this red sources are the newly identified brown dwarf candidate in IC 1396. This is about 1 kiloparsec distant object. So this is on the right side is a J versus J minus H. So you can see this brown dwarfs, this huge trail of brown dwarfs. So we are detecting down to 10 Jupiter mass in this object with a deep optical and deep NIR photometry. So here is the HR diagram of these sources, and so this is the brown dwarf, and essentially these are the new detections in IC 1396, and this is a spatial distribution of this new detection. And I just want to give you my time is almost
five more minutes.
Yeah, sure. So these are the possible IMFs. These are very preliminary. We are yet to publish papers on this. So possible IMFs towards the different star forming region, Taurus, Sigma Ori, and IC 1396. So we are reaching down to 10 Jupiter mass in all the regions. So for Taurus especially, this is the predicted if you fit a log normal mass function. Till here we know already the membership of Taurus. So we are extrapolating this part of the Taurus IMF. So our survey limit is 3 Jupiter mass. So already up to 20 Jupiter mass, the members are well covered in Taurus. But we are aiming at this part. So in this mass range, we are identifying nearly 27 objects. So if you place them on the IMF, we'll get a power law fit for Taurus. But this is very preliminary results. We are yet to finalize this. And for the other regions, Sigma Ori and IC 1396, this is how the IMF behaves in the low mass end. We also look for the stellar to brown dwarf ratio. So stellar to brown dwarf ratio, what fraction of stars can be in brown dwarf mass range. So this is essentially the ratio between 0.08 to 1 solar mass, those stars between that mass range to less than 0.8 solar mass. So this is a recent this is a survey by Music et al. In 2019 by photometric analysis. So for all these regions, so the brown dwarf ratio is essentially between 3 to 5 for all these regions. And one of the regions, Sigma Ori, we get the brown dwarf ratio as 4. Whereas for IC 1396, the feedback driven region, which is known for its feedback driven activity, we are getting very huge fraction. It's like we are complete down to 10 Jupiter mass. We have no issues of completeness, but still we are getting a huge fraction. It's nearly 20. So that means the number of brown dwarfs in that region is really less when compared to the stellar masses. And we are yet to finalize if it is a feedback influence or not. But this is one unique region where we see such a dearth of brown dwarfs, whereas all the region, it's more or less between 2 to 5, the brown dwarf region. And I would like to highlight some of my future thoughts. So far we are within the solar neighborhood within 1 kiloparsec or within 500 to 1 kiloparsec regime. So in near future, we would like to extend this survey or this analysis, brown dwarf analysis beyond solar neighborhood. So this is one of the low metallicity environments. It's a called DO25 cluster. I know some of you might be already familiar with it. So we have this VLT Muse observations taken a deeper observation. This background images from the VLT Muse R-band image. So you can see this is one of the spectra from the VLT Muse, one of the spectra. So it comes out to be M2.5. So our observation is sensitive down to M6, M7 spectral class. And we'll be soon looking at the brown dwarf properties in the low metallicity environment. This is known for its low metallicity environment. And we also have an accepted proposal for the cycle 1 observations of JWST in one of the extreme environments towards the galactic center. So we'll be we will be essentially sensitive down to the extreme low mass in brown dwarfs and all. So that is our one of the ambitious program for future with the JWST. Yeah, here I would like to summarize the major results. So we are doing a survey of nearby star forming region with the W-band CFST along with the J and H broadband photometry, and we are aiming at a detection limit of 2 to 3 Jupiter mass for the nearby star forming regions. And we also perform the follow-up spectroscopic observations, and we confirm some of the new detections of these nearby regions. And preliminary analysis of torus shows that it's a power law form of IMF is more favored when compared to log normal. And some of the candidates with the Serpent South, it's one of the nearby star forming region with a very young active star forming region. We have identified them with the disk, and one is an active accreting binary system, which is also in a binary system with a companion at a distance of 45 AU. In surveys ongoing, we have follow-up observations already partially done with HST and CAKE, and in future we'll be doing more observation. And as part of the future program, we like to address this binary fraction and nature of companions, and we like to address this galactic center and low metallicity environments using bigger class facilities. So here I like to thank you for your attention, and I'll be happy to take any questions.
Thank you, Jessy, for a very nice presentation. Now this is a time for question, comments, feedback. So I encourage the participants to either unmute themselves and ask the question, or maybe you can type the question in the chat window or just raise the hand and then I'll call you. Yes, Ravinder, go ahead.
Okay, thank you. Hey, thanks, Jessy. That was a good talk. I want to know these the low mass limit detection of 2 to 3 Jupiter mass objects that you are seeing. Is it possible to confirm whether they are free floating or they are gravitationally bound to any other star?
If they gravitationally belong to any other star, we need to have that brighter companion, right? So we don't have any companion or nearby star. So we particularly visually search for the nearby objects. Also, we subtracted, we had some PSF model, and we try to subtract it and see even more fainter objects are in their vicinity, but we don't see them in the neighborhood. So these are like essentially free floating low mass objects.
And I actually joined a little late, so I just want to know, how do you calculate the mass of these objects?
These objects, once you have, so we have to rely on the HR diagram and the model. So once you have the spectral class, first thing is spectroscopically we need to classify. And then we need to, so once you have the spectra, you know the temperature, because spectra and temperature, we know the relations, empirical relation we use. And once you know the temperature, you have the bolometric correction for that temperature. And then you have to essentially put them on the HR diagram, then use the models. So, and HR diagram will give you the mass with the model.
Okay, thank you.
Yeah.
Smita, please go ahead.
Yeah, hi Jessy, very nice talk. I have just one question regarding the stellar to brown dwarf ratio you showed, right, in one of the regions of around 20 So, like you say that it is due to feedback influence. Maybe I missed it. Do you see the IMF variation also in this region?
IMF variation we don't see because we only fit a power low. We fit a globe normal form which essentially tracks you down to the low mass end. So we have to fit a separate power law here, and we have to have a power law here for the top mass end. So we instead of what we did is a log normal fit, but if we separate out the low mass end and the high mass end and separately fit the power law, then only we'll get to see if there is any difference in the power in the IMF. So as of now, it's just number. We have the mass of individual sources, and we got the ratio between the different masses.
Oh, okay. Okay. Yeah, thanks. And just one more thing. You told many of your sources don't have Gaia counterparts. Is it because they are fainter or?
Right. They're extremely faint for Gaia. Gaia reaches down to 2021 magnitude, but these are in R band. If you go, these are, for example, R band. If you see, they're like a 22 to 26 magnitude. So they are not detected in Gaia. So here is the essentially this yellow sources are the Gaia, and the red ones are not detected by Gaia. And this is the low mass NC. Here up to yellow, this is the Gaia detection, but our brown dwarfs are much below that. So we don't have Gaia counterpart.
Okay. Yeah, thanks.
Arpan, please unmute yourself and ask the question.
Yeah. Hello. Am I audible?
Yes.
Yes, please go ahead.
Hello, ma'am. In one of the slides, you showed one cube value. Can you just explain that again, please?
Okay, so this is I didn't explain completely about the technique. For that, I suggest you because of the lack of time. So maybe. Yeah, so I refer you to these two papers, Allers and 2013 and Allers and Liu 2020. So they have explained this method. So what they do to define this Q index, so for the non-stars, they take the synthetic photometry and then they find the ratio in this bands. So they have the non-stars, they have their spectra, then they make the synthetic photometry and then they find the ratio. So only for low mass objects they find these low mass objects have Q index minus 0.6, and all the high mass objects they lie essentially with a high Q value. So that is after that, in order to validate that technique, they did it on nearby star-forming region IC 348, where again it had a spectroscopy confirmation. Prior to this method, there is already spectroscopically confirmed members, because this is one of the very non-star-forming region where everything down to brown dwarf or even lower than that is well characterized. So for that non-region, they validate their technique with this filter, and then they got 90% confirmation rate.
Okay, ma'am.
Okay, so Varun, please unmute yourself and go ahead.
Thank you, Jessy. I have one question regarding the binary sources, binary subdwarf systems you mentioned. What are their companions? Is it a main sequence star or an evolved star or compact object?
No. It's also same young object. So so this is the binary system, which is HST photometry. So you have in one of the filters, if you see they can be. It's very difficult to separate them out. They're essentially joined, which is within less than like a 0.09. This is the 0.09 arcsecond is the difference between these.
0.09.
Yeah. Yeah, it's too close by. But we use the PSF models. We model the PSF in the field region, and then we scale the brightness of each system, and then we subtracted, and that's how we could separate out their distance. So their distance is 45 AU, and they are also, both of them are like have to be in a young system, no, because they are not these are a very young regions, star-forming regions. This is in serpents. Serpents is like a hardly 1 million year. The age is roughly 0.5 million year. That's where they all lie here. They are like very young system. So this companion also have to be in the pre-main sequence. It cannot reach the main sequence for now. It's in serpents.
Okay. Thank you.
Yeah.
Yeah, Sujan Dada, go ahead.
Hello, Jessy. Can you hear me, Jessy?
Yes.
Yeah, it's a nice talk. I have one comment related to Ravinder's question and one question related to your observation. The first thing is that the mass determination, when you do it from the evolutionary model like the mass luminosity relationship, it becomes highly ambiguous because we do not know the initial condition of this object, how they are born. They are really born like a star or they are born like a planet. But if you have a spectrum, then modeling that spectrum will give you very precisely the surface gravity. So you can precisely tell the mass range only if you have the spectrum of that.
Right.
So that is the way we determine the mass range of it, because it is sensitive. The models, the spectrum is sensitive to the surface gravity, and from the surface gravity, because the sizes are mostly fixed, it is of Jupiter size. And from the electromagnetic consideration also, we can tell that the sizes are like Jupiter.
Yeah, I completely.
Yeah, so that is the comment on the mass determination. The question is that some of the coolest object at that wavelength where you are doing the water, that is 1.4, but at 1.5 you get signature of ammonia. Have you
no, but ammonia presence is only for the old system. These are very young system. They do not have ammonia.
Yeah, so this is, I'm telling that if your effective temperature is less than 600 degree Kelvin, so then ammonia cloud will start forming and you will get it. But if it is quite young, means your temperature is quite high, then you won't get, of course, ammonia. It will evaporate or it will be in the visible. But if you are going for the coolest one, as you are repeatedly mentioning coolest, we divide it into 3 classes, these brown dwarfs, right? L, D, and Y.
Right. Yes.
So in white dwarf, you get ammonia thing like lumen 16. You find out ammonia, and there are some other recent result in 2020 and 21 where ammonia cloud is present. So when you analyze the band, so you have to be concerned about what temperature you are taking.
Right, but these are like a very young system. As I mentioned, it's a few million years. So unless they evolve into the later system, we won't expect ammonia in their environment. I completely agree. When they reach to white dwarf stage, they have the presence of ammonia, which I explained in the one of the slides, in the very first slides. So I completely agree that. So we don't expect brown like ammonia contamination in the water band for this kind of young system. So that is addressing your question. And regarding comment, I completely agree that there are discrepancies or ambiguities in the model explanation of this, especially this low mass range. And as you suggested, surface gravity, measuring the surface gravity is the right method to obtain its mass and characteristics for the characteristics. But we have the observational limitation because we can only use the low resolution observation, because when you opt for the high resolution, your signal will be very poor. So you have to have the low resolution observation not to get a better signal. So this is like our current limitation. But I completely agree that unless we have more surface gravity features, by model based mass estimation may not be, it's a very crude way to measure the mass. That I completely agree with you.
Yes, Neelam, please go ahead.
Yeah, hello, Jessy. Very nice talk. I have one query. Means just you cite you have shown the work by Music et al. So they have also used the photometry to determine their to select their brown dwarf or other substellar mass objects. So they have used the a control field observation. So can you also try with this IC 1396 the same?
Control field observations, right? Yeah. Okay, that is a good suggestion. But we are so IC 1396 is a where is it gone? Let me. Yeah, it's a Subaru observation. So if you go to the field of view, so this is a Subaru field of view. We have 2 pointing. Each one is about 1.5 degree field of view. So we had 2 pointing. But this bubble, if you see, it's a 3 degree. Yeah, diameter wise, it's close to 3 degree. So we are within our Subaru observation is within this bubble area. So unless we go beyond, much beyond, we cannot get a proper background, or what to say, the control field. But that's a good suggestion. I can try that. We didn't try it yet. But the problem is when you have a field decontamination, still it's a statistical what to say, it is not actually confirming the membership, right? It's just
just to calculate the mass function. I mean, if you want to calculate the mass function or brown dwarf to star ratio.
Right. I agree. Yeah, that's also possible. But anyway, along with the UKITs and optical photometry, we are reaching down and we are able to get a reasonably good SCD analysis. So I will cross check this with the control field. I accept your suggestion. It's a very good suggestion. We didn't think about it, but we'll look for the control field and we can validate our statistics with the control field suppression. So I'll definitely look at it with this corner side maybe.
Also, because these brown dwarf also emit excess emission in the infrared. So means, did you also get some extra like?
Yes. So this is for the serpents. We did check. We had only 6 new brown dwarfs in serpents. So out of 6, 4 of them are showing near infrared excess. So it's like a good fraction out of 6. If you assume that 6 are the only brown dwarfs, there can be many more embedded which we are not able to detect. But out of 6, we are getting reasonably good number. 4 of them are with the disk. So, but this is a very young system. Serpents is like hardly 0.5 or 1 million year. But as you go to a bigger age or longer aged one, the disk might have already evaporated. But this is also an young system. It's only 2 to 3 million year. So we are yet to perform. It's like a very preliminary analysis. We are yet to perform the disk fraction or disk analysis for the low mass end. But we'll be looking forward to it. But we don't have another caveat is we don't have longer wavelength observation, Spitzer observation for this. And why is this is a 1 kiloparsec object? So why sensitivity is not sufficient? So Spitzer do not cover for the larger area, but I have to still look at the longer wavelength observation. So we haven't done it yet.
Okay.
As of now, it's only Subaru and UKITs observations we used.
Okay, thank you.
Yeah.
Okay, so if there are no further questions, so let us thank Jessy. Thank you very much, Jessy, for accepting our invitation and joining and delivering the seminar. And everyone for joining, and then I hope to see everyone next time. So bye-bye and have a nice day. Enjoy.
Yeah, thank you. Thank you all.